ingenieros, Daniele Peila y Carmine Todaro. El profesor Daniele Peila se graduó como ingeniero de minas en 1987 en el Politécnico de Torino, donde después de un periodo como ingeniero de campo en empresas de construcción, se convirtió primero en asistente de investigación y luego en profesor. Actualmente es profesor titular en el Politécnico de Torino y enseña túneles, refuerzos de suelo y roca. Es director del máster de posgrado sobre túneles y tuneladoras, presidente del laboratorio Túnel y Espacio Subterráneo. Junto a él, el profesor Carmine Todaro se graduó como doctor en Filosofía en Ingeniería Civil y Ambiental en 2021 en el Politécnico de Torino. Tras un periodo como investigador postdoctoral en el Consejo Nacional de Investigación de Italia, se convirtió en profesor asistente en 2022 y es coordinador del Grupo de Trabajo 15, Subterráneo y Medio Ambiente en la Sociedad Italiana de Túneles y vicecoordinador del Grupo de Trabajo 15 en la Asociación Internacional de Túneles. Los escuchamos.
Good morning, good morning, Mr. Peila. Good morning, Mr.
Good morning.
Todaro. Thank you very much
Good
joining us, and welcome to our Congress. It's a pleasure to have you here with us. I have one question. You have 4 presentations now within this training course. My question is, shall we split these presentations and make questions in between, or do we leave the question until the end?
For me, it would be preferable to have the questions after each presentation. I don't know what Elena and...
no problem. We can organize in between ourselves. So I also think it's better to make questions after each presentation, since the presentations are quite long and very, very intense. It's better to make questions after each presentation. So please go ahead, and after your presentation, we start with the questions. Thank you.
Excellent. I will share my video. If you wait a second. Okay, do you see my video?
Yes.
Yes, yes.
Excellent. So, my presentation, I go in the presentation mode. Wait a second. Oh, I'm sorry, I am in the wrong position of the presentation. Here we are. Okay, I will lead the presentation, and then I will ask to Carmine to say something, but I think that due to the time schedule, I will try to manage mainly the presentation. I was asked to deliver a presentation on just a collection of main hazards that can be found when tunneling in conventional and or mechanized tunneling. This was the task that Michel Defayet asked to us to manage for this short course, and I tried to fix to this schedule. Starting with the presentation, I think that is important to have a clear overview why to understand the risk of tunneling is so important. I think that all the people who work in tunneling engineering, when they approach to design, they do this, what I am telling, and I will tell in a second. But sometimes this is not structurally organized. So this slide, that this is mainly a course, is for me very important. Is that is fundamental that when we approach to a tunnel design, we understand clearly from each tunnel section, and not only for each tunnel section, but also for each construction phase, including the final state of the tunnel, and with experience, with computations, we have to identify and assess, and define which is the extent of all the constraints and the hazard. Because around the tunnel, as you can see here, around the tunnel, there are some natural constraints, also called hazards, that are related to the ground, to the hydrogeology, and to the environment. Then, when we have identified all the hazards that are present in our tunnel, it's clear that we have to choose and evaluate the proper mitigation measures. How to mitigate the impact on the construction of these hazards, and which are the goal of the mitigation measures, of the hazard mitigation measure. I divided in two concepts. One is, which is the goal for the hazard mitigation? Just to make a very simple example, is should I control the face stability, the tunnel face stability? This is the goal. So I have an engineering design to define which are the best tools and the technology and for example, the pressure to be applied if we are working with a machine for mitigating the engineering design, for mitigating this hazard. The other topic is how to achieve this goal. And this is mainly related to technology. The two aspects are joined together, but can be thought as two pillars of a correct design. Then only when you have understood which is the goal and how to achieve this goal, you can go through the design. So design the support, design the auxiliary measures, design the excavation method. Altogether, this process is leading to the construction method. Now, after this general scheme that I will try to explain a bit better with an example, now I answer to the question that Michelle asked to me to discuss, which are the main constraints that in conceptual design practice we have to face. There are engineering constraints that derive from the use and operational requirements, and very often are detailed and linked in national or international standards. For example, the geometry of the tunnel related to its use, the maximum slope, the curvature that you can accept if you are in a road or if you are in a railway, in a high-speed railway or whatever. Then you have the technological constraints that derive from the geology and the geomechanical of the soil and the hydrogeology of the water underground. I will make you some examples very soon. And they can be globally called as a geo, linked to the geology and the geomechanical hazards. Then there are environmental hazards that are constraints depending on the local environmental conditions. Then there are specific hazards related to the excavation method, excavation and or support stability hazards, and operational health and safety that are frequently underestimated, not considered in this process, but to my opinion, they are a key point to be taken into account. Then you have logistic constraints that can become an hazard, that in certain area, for example, you don't have enough space for the job site, for the construction of the machine. So you are forced to go underground instead of staying outside to construct the machine. The management of the excavated muck, particularly when it is polluted, and all the supply and management of what is important for the technology method and the machinery. And then last but not least, socio-political constraints that can be that the population do not want a specific construction in that area. Moving to the most hazard related to the tunneling, that is the core of our seminar. The excavation hazard are all related to the construction phase, affecting both the spatial domain close to the tunnel and what is very far from the tunnel. And you can have hazard that can be mechanical, hydraulical, physical, and chemical, and we will see them later on. Then you have operational hazard, environmental hazards, and health and safety of the workers. I will not talk about the operational hazard that are the hazard during the operation of the tunnel. That in Italy, in this moment, is becoming more and more important, related to the maintenance of all the tunnel and the movement that can occur in all the lining made of concrete can affect the safety of the roads, but this is out, so the operational hazards are out of my presentation. When we go to the mechanical hazard, so the geohazards, we can have tunnel face and cavity collapses, both lined or unlined. Detachment of unstable rock wedges and potential local collapses. Caving that can evolve with the development of chimney up to the surface. Reactivation of large dormant landslides. Slope stability at the portals, rockfall, avalanches. Sometimes this aspect of the slope, of the stability of the surface is not considered as part of the design of a tunnel, but unfortunately, in many big projects, the risk of rockfall and the large landslides can affect the job sites, can affect the entrance of the tunnel, and can require specific design. And our knowledge is, as a tunnel engineers, is frequently not enough deep or give enough attention to this topic. You can have an acceptable tunnel cavity displacement in squeezing ground. You can have a karst. An example of the karst you have seen in the presentation that was done before this session. Rock burst, that is a typical problem of very deep tunnel, like in the Alps or in the Andine zone, for example, to think to Argentina. Then can be damages induced to existing structure and underground infrastructure by vibration and by displacement. And hazard that can affect the production of a TBM. Clogging, hard rock, variable ground. I will focus on them because it is quite important. So also a TBM management can be affected by the geological property. Clogging is for clay. Hard rock can prevent a rock TBM to do the foreseen penetration. Variable ground is a complete mess. These are directly linked with the geo condition. But if we go to hydraulic hazard that can be related to the near field, so the area of the tunnel, that is large water inrush that can affect the safety of the workers, but also related to the far field, for example, variation in the water table level. So will the tunnel excavation affect the water table level that can affect the management of the water resource that today, with all these climate change problems, can be considered as important and must be considered always much more important. Just to give you an example, I'm presently working in the Mont Blanc tunnel, that is a deep alpine tunnel in this moment, and we are finding that in a certain zone at 1,000 meters deep, the water coming there is around 5 degrees. So at 1,000 meters, a water 5 degrees, the only explanation is that there are some cracks, some faulted zone, and the water coming down is coming directly from the melting of the glacier on the surface that is going very quickly downstairs, down the tunnel. And this is important to take into account for the maintenance and, for example, in the case I'm talking about, the refurbishment of the tunnel. Sometimes the chemical and physical hazards are not deeply considered, but you can have rock mass containing aggressives of dangerous agents. You can have gases Methane is the classical example. Or you can have pollutants that the most important example that we are facing in alpine area is the asbestos, that is very dangerous for the workers, but it is creating a lot of problem in management of the excavated material, because the population do not want asbestos waste disposal, and how to transport asbestos-bearing rock through urbanized areas. But also sometimes high temperature during the excavation. It's very rare to have a very low temperature, but this can happen also in the north areas tunneling. This chemical hazard and chemical and physical hazard can also affect the safety of the workers. In the construction tunnels that are occurring between Genoa and Milano, in these days, high-speed train, they are crossing a zone very rich of asbestos, and the excavation conventionally there is quite critical, and the need of using a machine, for example, a slurry machine in that area, can be very helpful to avoid that the asbestos can go free in the air in that zone. So this is also part of the environmental constraint, but the environmental constraints are also linked to architectural and landscape consideration, because now in Italy we are designing a new highway tunnels and infrastructure closer to Genoa, and that is a very urbanized area, and all the landscaping conditional can be important, but water and air issue towards the population are again an important, so the dust and also the presence of ground contamination. If you have to excavate a tunnel through a zone where there was historically some industrial infrastructure that could have polluted the soil. Then there is the natural impact on the biotypes this can be very critical in mountainside areas, and also correct natural resource management is also today, with the concept of sustainability of an underground and of a global construction, is becoming more and more important. So this very wide overview leads to this slide. Due to all the risk and constraints, to all the hazard that can lead a risk, require that the risk management approach should be developed. So when the risk level due to the hazard is not acceptable, you need to design a proper mitigation measure. And this is the key issue of the design. You should have an hazard mitigation measure that should be identified and then designed. I always divide the concept of identify and design, because identify is to understand which is the best. Design is to enter in the detail of the structural, or not structural, but of the technical frame of the system. After the application of the mitigation measure, there is also always a residual risk level that should be defined and eventually accepted or shared by the various actors. And this is in a tool of which Elena will for sure discuss later on. And then you need to think to a contingency plan in case of failure that should be identified and designed. So just to summarize the key concept of the geohazard, the instability condition that can occur around the tunnel depends on the type of soil and rock, to their mechanical properties, in which the excavation is done, and the natural pre-existing state of stress. So it's not only the properties of the rock, but it's also the state of the stress. So if we think to a rock, you see that you have a very low overburden, so very low in situ stress. You have a stable area that can move, increasing the fracturing degrees, but without increasing the in situ stress, towards unstable wedges and towards potential caving. But if we increase the deformation, fracturing degrees, and in situ stress, you can have a large convergence that can arrive in squeezing. And if you have a very stiff rock, you can have a problem of rock burst or limited problem of spelling. This is a very famous picture that I have a little modified from that. It's clear that all these phenomena that can occur around the boundary of the tunnel can impact both the local stability, the safety of the worker, the lining stability. In the case of the boundary displacement, this can affect also the surface stability. Going back to another slide that has been frequently shown in ITA presentation, this has been taken from a presentation from Grasso of some years ago, but is always active. You see that from the when you have identified the hazard, you go to the choice of the excavation method, conventional, mechanized, and you have the mitigation measure. I don't want to enter in this detail. Just to show you an approach, a global general approach, you see that from the hazard, you go to mitigation measures. For example, we wanted to excavate a tunnel full face. This is the, oops, I'm sorry. You see, this is the direction of advancement, and you see that there is an hazard, collapse of the face, as in the picture that occurred, and collapse of the free span. This is an excavation conventional. So the hazard management goal is to prevent the face collapse. How can we do that? For example, the possible mitigation measure is to reduce the height of the face. This is the approach using a partialized face. In this scheme, the engineering design is to evaluate the free span here and the head and bench side. And then the technology is to how to excavate and with which type of support. It's clear that we are changing the situation. There are new stability hazards that can occur. One example can be problem of instability of the footing of the steel arches. So you have a new engineering design, evaluate the type of footings and type of underpinning, and the technology is which type of foundation of this steel arch you will have to use. Also, you have to take into account that there is a new health and safety, operational health and safety, that there are more interfering workplaces, a workplace here, and this will increase the risk for the worker. Another choice that you can do is to use a possible mitigation measure is to use a shielded machine, full face machine able to apply the face pressure. Will be the face pressure will prevent the collapse. So you will have to evaluate the pressure to be applied. The technological choice, as I explained in my first slide, is to choose the proper type of machine. Again, when you make a choice, you have a new hazard. For example, the new stability hazard is how can I manage the face properly, the face pressure at the face with the machine. And the new technological hazard, for example, if we are working with an APB machine, is the management of the soil conditioning. So the new technological hazard is, should I choose the proper management of the soil conditioning? I have some slides discussing this concept. Environmental hazard, again, a new environmental hazard that depends from this technological choice is how should I dispose the muck, for example, with the machine. And another possibility with the same type of hazard, the management of the face, is I can use auxiliary methods: drainage, press support, jet grouting, permeation grouting, ground freezing, soil reinforcement. So I will create a new type of material, press supported, and they can be done from the surface, from nearby underground structure, or from the face. Again, the engineering design is to make the design of this improvement, from where and to which extent. And the technology is the technology of this intervention. For example, if I'm working now in a tunnel where we are injecting a sand that not everywhere is possible to be injected. So instead of using the permeation grouting, you can go with jet grouting or whatever. But the concept I want to highlight in these methodological slides is that the engineering design is different from the technological design. I have here collected some examples. I have 35 minutes, I think, of my presentation. So I ask to Carmine to send me a note when I am going close, because I lost my presentation. Okay, Carmine?
Okay, Daniele. We have
so it's 25 minutes now, so I have 10 minutes to go. So,
yes.
For example, here you have the squeezing that are some example from the crossing of the Alps in the Turin-Lyon on the right, and you see that how much the tunnel has been closing. Then you have some example of rock burst against from Alpine tunnel, where you had the detachment of the big elements due to occurrence of the detachment. Here you can see the slabbing of the shotcrete due to the rock burst. But also some example of what I was trying to explain, the risk of interference between surface instability and the tunnel. This was a very old picture that was given by my mentor, Professor Pelizza, many years ago, where during the, you see, it's a very old picture, but for me, it's very pedagogical, where you see the slide collapse that affected the portal entrance during the construction. So it was not a proper evaluation of the stability of that. This is another example I'm working with, again, sometimes underestimated in the tunnel design, where here you have a cliff, here you see the cross section, and the detachment of potential blocks that can affect a tunnel portal. And the risk here of the tunnel portal is during the construction, but then also during the exercise of the tunnel. And here you see all the design that we carried out with the wire mesh, like that one. This is the numerical model of a mesh we carried out. And here you have the study of the proper positioning of the mesh to protect the exit of the tunnel, but also to protect the worker that will create this artificial tunnel for the safety of the traffic. So you have two concepts we take into account. In this picture, you see the protection of the entrance of the tunnels, also with the wire mesh. Here you see the cliff, but this is another example of the protection of the job site due to the rockfall condition. So you have to protect our workers like that. Water, here you have the example of a very heavy water income. Here you have an example of a sinkhole that were created during the excavation of the tunnel for a not proper face management. This was an excavation with an APB, but the concept is that there was not a proper face control of the face, and you have a sinkhole reaching the surface. When we think to the hazard is also the stability and the detachment of wedges due to the presence of the joints. This is a typical picture of the geometry of the hazard, but this is an interesting example where you see that this tunnel was excavated with the original, with this size, with no large problem of stability. But when there was the enlargement of the excavation here for the parking zone along the tunnel, due to the exercise, the joints that occurred created a very wide possibility of detachment, and there was this collapse that was not occurring along the tunnel, but the geometry of the joints were more or less the same, but was the enlargement of the tunnel. Again, these slides were given to me by Professor Pelizza. Then I don't want to enter in the karst problem that was already discussed, but also the sudden rush of tunnel that can completely flood the tunnel. This is an extreme example. I want to give your attention to this example, that is the tunnel in Catania, in the metro of Catania, where you see the complexity and the many hazards that can affect this excavation, because you have here a strong basalt due to a lava flow that was coming from the volcano, and here you have the sand that was affecting, that was deposited above the lava flow. But the stability of these elements are completely different and require different approaches to different hazards. But globally, they describe the hazard of this phase, of this problem. This is another example in the south of Italy, where you have different layers of sand and clay, and these different type of layer are different hazard, because the clay is stable and the sand not, and so you have that this slab of clay can detach or can collapse. In this condition, there was a fatality that occurred. I have then we move to rock TBM, and generally speaking, you have tunneling in geological and normal geological conditions. So when a TBM advances with the foreseen condition, but when you go to special adverse geological condition, you need to add something, because the condition need to be faced, so you have to change something in your excavation process. Then there are the critical events that will block the machine and require important measures to allow the restart of the excavation. I want to tell to you that the hazard scenario and the phenomena that can be encountered in long and deep tunnels, and that can lead to adverse condition and critical event, you can find an ITA Working Group 19 report, where it's quite comprehensive and quite wide, and you can have here these are all the scheme that I have added in my presentation, and I will skip all of them, but you can find all these slide there. Here to show you some example of critical example, since I'm running out of time. In rock TBM, had a rocky block fracture in variable condition at the face, can affect the stability of the face, but mainly will affect the durability of the cutters, so the cost of the excavation. These are typical example that you can face. Here you have, again, the same type of problem that occurred in conventional tunneling, the detachment of elements moving from the surface due to the presence of joints. And here is an example that I have personally studied, where this slab, not very big, but was laying on the machine with a lot of problem of safety of the workers. Then you have a squeezing of rock mass that can affect strongly the excavation. But on the other end, when you are working with rock TBM, when you have a massive, very hard rock, you have no penetration. So the presence of very hard rock with abrasive soil and a lot of quartz, this will lead to a lot of a problem. Also here you have an example of a large squeezed gem. I will jump all this part, and I will move to the soil TBM. So that is totally, I will be very fast, no more than 5 minutes. And a soil TBM, I always think that is a global machine that should take into account the surface and the underground. So you have a problem of stability of the face, you have a problem of movement of the soil along the shield, you have the problem of correct backfilling behind the shield. So this global system leads to the subsidence and can affect urbanized areas. So the geological risk that can occur in this condition is that if you don't understand the interaction between the machine and the soil, you will have a lot of hazard. This is, in my opinion, the most critical concept to be taken into account. Not proper understanding, because it is not the machine working and the soil answer to the work. It's together that if you don't understand globally the system made by the machine and the excavation technology, this will affect and create a lot of hazard due to this condition. And particularly, and sometimes underestimated, is the critical aspects of the conditioning of the soil. The condition of the soil. Today, the APB machines are the most used machines all over the world. And when you are excavating using this machine and you don't deliver a proper analysis of the conditioning, then you can go to very large risk of, so the hazard of a not proper conditioning of the soil in soil excavation is really dramatically high. I just collected here an example of a problem of thickness of a clay that we found in Italy. We studied in my lab, in our lab with Carmine lab. These were our tests developed by Carmine in the last couple of years. And in this example, you see that a not proper conditioned clay was sticking to the bowl, and you can imagine what can happen in the machine. But if you do a proper management of this risk, the clogging risk, you can see that the soil is becoming like a good paste and the APB will work properly. So when you move to soil machines, the first concept is that it's not a single machine, but it's the soil plus the machine. And you have to understand clearly the technology. And particularly, I have to highlight that all the problem that we have found was not a proper management of the soil conditioning. So I am prepared a very wide presentation that you can read, and you have some more collection. And I thank you very much for your attention.
Thank you very much, Daniele. Now we continue with Carmine.
No, Carmine, we just decided that to skip from one to the other was too much wasting time. The presentation was prepared together, but then we choose that it's better that they all do the presentation.
Okay, excellent. So before we start with the second presentation, I think we make some questions. ¿Hay consultas a esta primera disertación? Por favor.
Hacemos como siempre, si tienen consultas, la pasan por escrito, nosotros las acercamos aquí al panel, si no, continuamos. Sí, muy bien, me dicen que sí. Entonces vamos a continuar con la siguiente oradora, que va a tomar el tema los conceptos de gestión de riesgos aplicados a la gestión de proyectos de túneles, que será llevado adelante por la ingeniera civil Elena Chiriotti. Le voy a presentar. Elena Chiriotti es graduada de Ingeniería Civil del Politécnico de Turín en Italia y obtuvo un doctorado en mecánica de rocas en 1997. Luego de pasar 11 años en Geodata Italia, empresa de ingeniería especializada en el diseño y supervisión de la construcción de obras, se incorporó en Sistra, Francia, en 2007, donde permaneció hasta 2015 como directora del Departamento de Túneles y Estructuras Subterráneas, dirigiendo un equipo de hasta 70 ingenieros. Desde diciembre de 2015 es cofundadora y directora ejecutiva de Incas Partner, empresa de consultoría con sede en París y actuación internacional en el dominio de cuestiones técnicas, estratégicas y contractuales relacionadas con obras subterráneas. Elena es miembro activo de AFTES e ITA y participa en varios grupos de trabajo nacionales e internacionales, redactando directrices y recomendaciones sobre obras subterráneas. Desde 2016 es la animadora del grupo de trabajo 2 de ITA, así que la escuchamos si le parece.
Hi, Elena. Welcome to our Congress. Thank you for being with us, and we listen to you.
Let's activate my micro. Thank you very much, everybody. Good morning, and thank you very much for this kind introduction. I go directly to the theme of this presentation. I've organized it in 4 key points. So in the first one, I would just like to address the general principle of risk management for underground works. And I really hope that everything I will say in my presentation is something that is not at all new for you, because if this is the case, we can, as a worldwide organization of practitioners, say that risk management nowadays is a part of our practice in the underground projects. So first of all, a quick overview of what ITA has produced, the International Training Association has produced on risk management in the last year. There is a real ITA engagement towards the risk management related issues, and this started in 2004 in the working group number 2 that I now am animating, in which the principle of risk management are described, and all the process for the identification, analysis, and communication of risks is addressed, and also responsibility of parties. We are now reviewing in working group number 2 this publication and working in complements on that specific guideline. And then you may all know that in 2019, the FIDIC Emerald Book was presented, and this was a collaboration in between FIDIC and ITA, a very successful collaboration in which the yellow book, the design and build yellow book of FIDIC was readjusted to take into consideration specific facts related to underground works. Among these specific features that are included in the Emerald Book, we can list the fact that in the Emerald Book we tried to, I say we tried because I was one of the reviewer of this book. We try to introduce the geology and the geotechnical in a different geotechnical aspect in a different way. So we believe that all the geological and geotechnical data have to be disclosed to the tenderers and the bidders as global information for information only, and then that a geotechnical baseline report has to be prepared that includes the contractual limits and the condition that are anticipated to be encountered, so that a limit can be set in between what is expected and what is unexpected regarding the condition of the ground. And then there are interesting remeasurement clauses that allow the contractor to be paid for the works he has done and which are influenced directly by the underground conditions, by the definition of excavation support classes and the possibility to adapt these classes to the condition encountered and to be paid for that. And in association with that, the possibility of clauses for the adjustment of the schedule of the project. So the adjustment of time, so that the time can be reassessed during the project. And we think that this kind of approach is a fair approach for both the employer and the contractor. Is an approach in which risk is shared in a fair way. Then in 2021, working group number 3 published the ITA contractual framework checklist for subsurface construction contracts. That's in spite of which form of contract is adopted, prepares and explain a list of fundamentals for the management of underground works, including risks. And in 2023 appeared the review of the Code of Practice for Risk Management in Tunneling Works. That is a work prepared by the International Association of Insurers and ITA. So a real engagement of ITA in these activities related to risk management. What the management of a tunnel projects include managing different aspects that are strictly related to the management of risks. We know that underground works are affected by subsurface variability of ground and hydrogeological conditions. So this the control of this variability is strictly related to the quality of the site investigation and to the resources and time we allocate for that. We know that we have to have a robust geo model, geotechnical, geological, hydrogeological, to help our capability to predict the expected behavior of the ground when the tunnel is excavated. We know that the functionality of the design is strictly related to safety, and the two of them impact on the layout, on the alignment, on the cross section, and on the ancillary works. The construction methods are strictly related to the anticipated conditions and the constraints of space and geometry. There are all the issues related to the access, to the logistic, to the environmental impact, to the cost and planning, and in all of these risks enter and risk have to be assessed. And we really believe that with the experience, the capacity to anticipate events, and a full operational risk management approach, projects involving underground space can be dealt in an appropriate way. The principal risk management attributes of project involving tunnel works. Well, ITA in general encourages the implementation of a formal risk management, and this independently of the form of contract that is adopted. That means if it is an Emerald Book form of contract or if it is another form of contract. And in each of these, in any kind of project and in any kind of contractual approach, there are principles that should be respected as regards underground works and risks. First of all, it is up to the employer to initiate in the early phase of the project a risk management process for the project. The formalization of risks should follow the preparation of a formal risk register in which the initial risk, the mitigation measures, the residual risks are identified and then allocated to the parties. the recognition that risks are strictly related to costs and time. And so these three items cannot be dealt with independently. They have to be integrated, and an integrated analysis of cost, time, and risks should be asked to the contractors, and should be prepared and prepared since the early phases by the designers. Then the real belief of the professionals that nowadays we assist to the fact that, for example, for mechanized tunnels, the different type of machines can more or less address the same kind of ground conditions. So the ground condition is no more the big barrier, the big differentiating aspect to choose one machine or the other, because there is a almost overlapping domain of application of the machines. And so actually the devil is hidden in the details. So what we have to focus our attention is all those risks that could be characterized by a high impact and a low probability, because when they occur, they will block our project. The preparation of a geotechnical baseline report to distinguish what is expected and unexpected conditions, and to have a clear view from the technical and contractual point of view. And then the mechanism for adjustment, the remuneration, and delays, as we were mentioning before, speaking about the Emerald Book. And principles that are very similar are also addressed in the joint publication from ITA and the International Association of Insurers in the Code of Practice. What is stressed, and I think is very important, I took some extras that are speaking to me. The competence of resources, whatever we can do in a project, the first thing we need is competence. And the second is the appropriate contractual mechanism and definition of role and responsibility. So the heart of the overall mechanism is in people and in how we manage the works. The collaborative risk management among the parties. So risk management is not a document that we have to prepare at the end of the project and then forget about it. No, it should be a driven factor, a steering factor of a project, and so used to steer the project in a collaborative way, and should be extended from the design through the construction and to the life cycle of the works. The importance of site investigation, the importance of clear contractual documentation, and time. We need time to properly do site investigations. We need time to properly assess risk. We need to give the tenderers, when we bid for underground works, enough time to assess the technical risks, so that the impact on the project can be possibly reduced. And then sufficient instrumentation and monitoring to control during the execution of the works. Sorry. Here. So the main components of a proper risk management approach: the definition of the risk policy with the owner. That means the acceptability level of risks, the mechanism of risk sharing, the contractual form. All these is part of the definition of the risk policy that is with the owner, and the designer has a main role in helping, in facilitating the decision of the owner, and this especially in producing a design and producing analysis by scenarios in this design, so that the impact of choosing, for example, one type of threshold for the building impacted in the geotechnical influence zone, the kind of threshold that we select, well, they can have an impact on the costs, on the delay, on all the aspects of the works. And choosing one value of a threshold, or one contractual value for a threshold, or another value, the impact of this should be clear for the owner. So it's up to the designer to show through his analysis what are the impacts of the different choices. So the risk policy is with the owner, but the designer is the right-hand man for the owner in this kind of process. And then the designer is the actor of the preparation of the risk register for the technical risks related to geology, related to construction, at the design phase. In France, for example, we produce two types of risk register before a tender. We produce the risk register of the design, in which we have the tracking of all the design choices that have been made and their impact in reducing the initial risks that were identified. And then we have the tender risks register, that is the one that is shared with the contractor, and in which we highlight what are the residual risks. And both of them are disclosed, the first for information, the second contractual. All these analyses are focused to allow also the owner to define his provisions for risk, identified risk and non-identified risks. And then there is the contractualization part, and in which the quantity and unit prices can be associated to predefined contingency measures, in which we can have a quantitative criteria through the GBR to activate the risk register lines, and mechanism to remunerate the occurrence of risk and adjust the time for the project completion. So we want to arrive to a comprehensive risk register, as we see, well, an example on the top of the screen. But we want also that during the bidding phase, the contractor is able to critically analyze this risk register and give his contribution and suggest amendment before the adjudication, so that the mechanisms for sharing the risks are as clear as possible before the start of the work. This will not reduce to zero the risk of claim, but will reduce significantly the risk of claim, and will allow to have a smoother construction period if the principles are applied correctly. One aspect that has to be asked, we believe, to the contractor is also to represent the duration, the impact of the risk on the duration of the contract on the project schedule. This can be done at least on the space-time schedule with regular updates, what in France we called a planning chemin de fer, and ideally by implementing a quantitative and probabilistic assessment of the risks, because risks, they have clearly an impact on cost and time that we can assess in a deterministic way or in a probabilistic way in the best situations. And as soon as we do it, the better for the project, because really the impact of the risks will increase on the impact of the risks, the occurrence of risks on the project time and schedule will increase with time, if not dealt with properly, and the opportunity to reduce the risk that we have at the early stage of the project is very, very important. And we have to try to stay in this scheme that passing from bidding to construction to then operation, our risks are reducing. Then passing for this to the second key point. The second key point relates to investigations, from the investigation to design and construction. So the earth of the design and construction process. I will not enter in the details, but just go ahead with these general principles that have to appear in our risk management approach. So key points that I would like to stress. The importance of a staged design. A stage design make possible for the owner to take decisions that are supported technically, supported by a number of analyses that are sufficient for the owner to take the proper decision, the best decision at that time for the project. So a staged design means also staged investigations available at this stage. This seems like a obvious statement, but it is not so obvious, because, for example, in the last year, we in the region of Paris, we assist to a huge increase of underground works, extensions of metros, extensions of regional railway lines, the Grand Paris Express. All of these works at the sudden all together put the word of site investigation in crisis. So we assisted many times to investigations appearing during the bidding stage. So the bids come out, the investigation for that phase are not yet available. The bidders have to work with the initial informations on geotechnics, and then the information come after. So this is not the ideal way of doing it. If we want to manage the risks, investigations have to be ready at the right time, to take the decision at the right time. So investigation, when I speak about investigation, I speak about everything that goes from the geotechnical and geological data to hydrogeology, hydrological data, topographical data, meteorological data, environmental data. And in the publication that we made a few years ago in 2015 with the working group number 2 about the strategy for site investigation and tunneling projects, we stressed the importance to have a proper amount of site investigations. And we did a statistical analysis of international projects, and this led us to say that less than 1% investment in site investigation and the preliminary design stage is generally considered to be risky. And what should be a good rate for normal project is about 3% at this stage of preliminary design. Of course, this 3% can increase a lot to much more than this when we deal with huge projects like Transalpine tunnels, 50 kilometers of tunnels, in which we have in the investigation phase to excavate experimental adits, experimental shafts, and so on. So this is just a graph to show how what is the relevance of site investigation in our projects. So site investigation, they should appear at the right time during the project, so that at each stage the proper amount of site investigation can be incorporated to increase our knowledge, the theoretical geotechnical knowledge that we have on the project. And what we do not want to happen is that starting from the preliminary detailed design, the investigations, the results of site investigation are taken into account too late. when they are taken into account too late, your knowledge, the geotechnical knowledge of the project will not reach the level where it should be, and this would be an element that can lead to major accidents. And so this is something that we do not want. So what we want is a good ground model with a proper technical interpretation. The model has not only to be complete, but has to be communicated in the proper way, and has to include all the parameters that are influencing the construction method. So many tools. We have many tools nowadays. We have 3D tools, or the classical mock-up of along the tunnel project, the tunnel alignment, that is still a very good tool, especially if we are able to connect the parameters of the ground to the risks and visually explain to all the parties of the project where the risks are, what type, and what could be their impact. Importance of construction method. Professor Peila addressed that. Tunneling is not a risk-free exercise, and the proper construction method is the key element one of the key elements to properly manage an underground works. In order to do the proper choice, again, the proper amount of site investigation, the proper approach to interpret the ground parameters, and also highlight what are the residual uncertainties, and then understand the intrinsic behavior of the ground. So understand what are the failure mechanisms. This comes from the experience, this comes from calculation. And sometimes we believe that the calculations are the reality. So we have to, as engineers, always to also do a step back and remember that our models are a simplified picture of our project, and remember of our past experience, and in order to identify properly the failure mechanism. The adequate construction method will come from this understanding. And then, of course, everybody knows about the two groups of construction method that we can use: mechanized methods, conventional methods. We know the advantages. I will not go on that field, but the choice of the machine, the type of machine, is not sufficient alone. APB, TBM, slurry, mix shield, dual mode machine. We will select the one that offers for the particular project the best control of the pressure losses, the phase stability, and the best control of induced settlement if we are in an urban environment. But then there are all the aspects related to the appropriate design of the cutter head, of the power, of the maximum phase pressure, of the conditioning for the APB, of the job site and logistic for a mixed shield or a dual mode. Once the design of the machine has been properly done, well, there is still something to say and something to share among the parties. And we really believe that what has to be done is that steering parameters have to be chosen. Can be the phase pressure, the thrust force, the injection pressure, the weight of the extracted material, the density, or whatever parameters. But it's important that these parameters are identified as steering parameters, and on these parameters, thresholds are defined. in order to understand what is a normal functioning and an abnormal functioning or some dysfunction in the works. So what we have succeeded to do and I consider this a personal success in France, is introducing in the French recommendation of AFTES the use of a plan for the advancement of the TBM that was developed first in 2001 on the Porto Metro. You saw the picture of the Porto Metro before. This is the arrival of the TBM in the center of the city, and this experience that we gained at that time was collected in a book that I co-wrote, that is Mechanized Tunneling in Urban Areas, in which I specifically wrote the chapters about the risks related to existing building, phase pressure and whatever. The idea of the plan of the advancement of the TBM, what is this? Is a document that is based on the construction design, and in which we summarize section by section of, for example, 500 meters, of 1,000 meters, what are the expected ground conditions, what are the expected groundwater levels, and what should be the steering parameters of the TBM with the thresholds of each of them. Then this becomes a document that is shared among the parties, so that we abolish this approach that methods are with the contractor only. No, they are part of the project, and they have to be their consequences have to be known and shared. These parameters are followed up together with all the other parameters of the machine, but they are key parameters because then on these parameters we will do a back analysis. And the back analysis at the end of the 500 or 1,000 meters will allow us to review our prediction, were they right? No, do they have to be updated, and why? And in this way, we construct a system that is auto-feeding knowledge in the project. And this is exactly what we want to do. So we now the use of the plan of the advancement of the TBM is contractually included in the majority of the project in France. Construction method. In case of conventional methods, the approach should be similar, and in order to again to control the risks that are related to these construction methods, choice of not only the proper choice if we go in full phase or partialized sections, not only the design of the phase stability, the analysis of the stand-up time and the advanced cycle, the definition of the primary support, control of groundwater, installation of the final lining type and when to install it, but also again defining steering parameters on which we can define thresholds, and we can control the behavior and the response of the ground when excavating. Extrusion, convergence, plastic radius, pressure in the support, groundwater pressure, settlement, whatever, but define parameters in order to pilot, to steer the construction of the tunnel. Implement a flexible design. Implement a flexible design. All of us recognize this as to be a set of primary support sections that are associated to a project, to a tunnel project, along the tunnel longitudinal profile with a zoning for these. For each of these support sections, a zoning that is predefined at the design stage. Very important to associate to this zoning an applicability criteria. So to have criteria to go at the tunnel phase, recognize the quality of the ground or the rock mass, and decide what is the section to be applied. But not only, we can go further. We can make this support section. We can make this support section slightly variable. So each of them, instead of being a set of fixed shotcrete thickness, number of bolts, length of bolts, can include a slight variability of these type of supports, so that the support section can be easily adapted on site, and that we have all the possibility of ground support already pre-analyzed, predefined, and associated to applicability criteria, so that we know when we are on site if we apply the ordinary support section or the heavier or lighter support section according to clear criteria. As much as we can do that, as much we will be able to manage our risk during construction. So,
sorry, Elena, we have to round up the presentation.
Yeah. So
Please.
just, yes, it's just everything, all of these has to be seen in a observational approach, in which monitoring plays an important role, if possible, to control everything in a unique platform, the TBM, the ground, the buildings. So we have this tool nowadays, and then was just finishing on the importance of the logistics. But maybe we can discuss of these in some questions that you can have, and otherwise you have at your disposal all the presentation on site logistic, and then the impact of risks on cost and delays. I don't know if there are special.
Okay, Elena, thank you very much. Yes, let us see if there are questions. ¿Hay alguna consulta que podamos hacer?
Ahí le acercamos el micrófono entonces. Por aquí. Está muteado, fíjese que tiene el botoncito.
Hello? Okay. The question is for Elena. Elena is Ricardo Andrade from Portugal.
Olá, Ricardo.
Well, je sais pas si on parle en français, on parle en portugais ou italien.
We can speak all languages between me and you. Portuguese, French.
Let's speak in English about our colleagues. Well, yes. It's about the documents. It's the first key of your presentation. Now, first of all, my congratulations about your wonderful presentation. Sorry. Secondly, I have a question is about the document about FIDIC. I manage a contract, FIDIC contract here in Argentina, and I would like to know if these conditions of the document, I think is from 2019, between
yes,
ITA and FIDIC.
ITA in Naples in 2019. Yes.
These documents is mandatory for FIDIC contracts, or it's only recommendations?
Nothing in what ITA does, and even if it is done with FIDIC, is compulsory. I mean, is one of the possibilities that we had. We felt in the ITA that there was really a need to review these contracts that were too much general for underground works, in which the risk and the fair sharing of risk in between the parties were not addressed properly, and we tried to adapt it to the underground works. So this is what we do. But I would not say if this is compulsory. If that is compulsory, what is compulsory? I would say, if you want your project to be insured, is that you respect the code of practice. I would say that that gives the general principle without obliging you to use a specific form of contract, should be a guide in our underground works. And this is why also the working group number 3 of ITA that prepared the Emerald Book with the FIDIC, they prepared this in 2019, and then in 2021, they reviewed the checklist, the publication of 2021, which is not related directly to FIDIC. And it is to stress again, if you do not use FIDIC, but your checklist to do the things properly are these ones, then it's up to you if you want to use it or not.
Thank you very much. Nice to see you again.
Nice to see you again.
Elena, one question from my side. In which extent these principles and this risk management strategy is being implemented by owners in general in Europe? How would you say, is this being
that is a very interesting question, you know.
Because as far as I can understand from our region, it is not very well taken into account and recognized.
Well, in Europe, there are different parts of Europe. There are north part of Europe, south, central. So we would say that who initiated all of these were the Anglo-Saxon. So they were slightly in advance to the rest of the community in Europe. But then, for example, if I can speak for France, in the last years, in the AFTES, the French Association of Underground Works, within AFTES, we did a huge effort to review this approach of risk management in the AFTES recommendations. And so now we have all set of recommendations and now I come to the answer, but just to make the picture. So we have all this set of recommendations that say how to do the risk register, how to associate prices, how to do this, how to do that. Then we expected few years, and then with Maud Macquarie, that is presenting also today, and with 4 other people, the AFTES president and steering committee charge us to do what is called the Observatoire des Pratiques Contractuelles, the observatory of the contractual practice. Because when you do a rule, well, there is a rule and there is the way to escape the rule. So how this was applied. And so what I can answer you is yes, the owner are using it. And are using it and seeing that this is a tool, especially at the design phase, to make more justified choices, also not only from the technical point of view, but also towards who finance the projects. So this is definitely an aspect. But then we could also observe that each of them has his own interpretation of it. And sometimes the risk registers are not too enough clear. Sometimes they are too prescriptive. Sometimes they are so detailed and so specifically related to a specific occurrence that if the occurrence is slightly different, you cannot apply the line of the risk register. So there is now in the profession in France, and we presented the results of this observatory last week in the Congress in Paris. There is really a rethinking of all of this to understand what went well and what has to be improved. So it's very interesting to participate in all this dynamic, but I can answer you, yes.
Yes, very interesting. And I think we have a responsibility as Tunnel Association here in our region to also to convince or to work in this direction.
Yeah.
At the end, it helps to reduce claims in contracts, no?
Yeah, well, sometimes, well, it should be like this, but sometimes what happens is some owners prefer not to activate these lines of the risk register, but to use the provisions to cover for addendum to contracts at the end of the contract, you see?
Yes.
Sometimes it's like an additional money that you have on
Okay, understand. Okay, is there any other question? ¿Alguna otra consulta?
Bueno, continuamos entonces.
Thank you, Elena.
Thank you very much.
Continue.
Agradecemos a la ingeniera
Bye,
Chiriotti.
Ricardo.
Vamos a presentar entonces el siguiente panel que tomará el tema de investigaciones geológicas y manejo de incertidumbres, características del suelo. Lo va a llevar adelante el ingeniero Tarcisio Celestino. El ingeniero Celestino es expresidente de ITA, es profesor de Ingeniería Geotécnica en la Escuela de Ingeniería de San Carlos y Universidad de San Pablo en Brasil. También es jefe del grupo de Ingeniería Geotécnica y Geología de Ingeniería en TEMAG, una importante empresa consultora de ingeniería en San Pablo, Brasil. Obtuvo su maestría y doctorado, grados en mecánica de rocas de la Universidad de California en Berkeley. Además, en la Universidad de San Pablo es responsable de los cursos de posgrado y áreas de investigación sobre mecánicas de rocas y obras subterráneas. Luego, sistema contractual adaptado, masterización de costos, lo va a llevar adelante el ingeniero civil Maud Macari. Maud Macari se graduó en la Escuela Nacional de Obras Civiles del Estado de Francia en Ingeniería Civil. Tiene una maestría en Transporte y Gestión Empresarial de Imperial College y Universal College London. Después de 4 años trabajando como gerente de proyectos en obras de vías navegables, se unió al Centro de Estudio de Túneles, que es el centro técnico del gobierno francés para estudios e investigación de túneles. Trabaja, además, en varios proyectos, túneles ferroviarios en contexto urbano y alpino, túneles de carreteras y zonas de montaña. Ingeniero.
Buenos días, Tarcisio. Bienvenido. Y
Buenos días.
Te escuchamos con mucho gusto.
Sí, buenos días, Martín. Mucho gusto estar aquí. Quiero disculparme porque debe ter habido un problema de comunicación. Yo estaba planeado lo horario que recibí para hablar a las 4:50 de la tarde. Entonces yo no estoy en mi oficina, no estoy properly dressed.
Lo lamento, pero estás perfecto, no hay problema.
Ok, entonces vamos a ver si consigo, como hago para, momento para share my screen. ¿Ve ahora?
Ahí está, perfecto.
Ok.
Ideal.
Entonces, mucho gusto, muchas gracias por la invitación. Y yo voy a preferir hablar en inglés porque hay algunos termos técnicos que yo sé que mi portuñol no sería suficiente. Entonces, I'm going to talk about geological investigation and ground characteristics uncertainty handling. The outline of my presentation, I will show the importance of geological conceptual model for planning and interpretation of geological investigation, the sources and types of geological uncertainty, quantitative consequences of geological investigation intensity, excavation safety and geotechnical uncertainty, assessment of probabilistic reliability, how to deal with this uncertainty, the spatial variability, how to deal with that with geostatistics, very simple concepts, brief concepts, I would say, and the use of ordinary kriging for spatial interpolation of properties, error estimate, and optimization of additional investigation, and some concluding remarks. Importance of geological conceptual model. It's unnecessary to say how important it is to have some knowledge about the origin and evolution of the ground mass, and a good geologist will have to be involved and bring this model to us. The role of faults, folds, and other filters, it's a danger of pure interpolations. This is the last thing that one should do, just do boreholes and interpolate information in between. The importance of outcrops, which in urban areas, sometimes it's very difficult to find unless you are in some peculiar cities like Rio de Janeiro, which is not usual. And finally, the role of a good geologist, as I mentioned in the beginning. These are examples of problems that we would face if we don't have a proper geological model. This is a dike. Let me put the pointer. A dia-based dike, very common here in Brazil and in many other locations. And if you just have a borehole here, a borehole there, and in the middle of what is good rock, you find this, and so many problems I have been involved with in tunneling related to dikes like this in Precambrian rock in Brazil. These folds, this is an example from the UK. If you don't have a clear idea about the model, interpretation can be meaningless with so many folds. Core stones, definition of the top of the rock mass is sometimes, we sometimes do mistakes by reaching a core stone and thinking that it's the top of the rock mass. And this has led to situations, I have seen designs in which people design for tunneling rock and you get there and it's not rock. It's just this type of ground mass. Or rotational landslides or faults in which we see that the continuity of layers, of horizontal layers, is broken. And all of this must be part of the model that the good geologists would use for the interpretation. Spheroidal weathering, also a big problem for definition of the top of the rock mass. And this type of rock mass would be, of course, much more problematic than could be anticipated just with a few boreholes and with a wrong geological model. Sources and type of geological uncertainty. Geological uncertainties can be of two types, aleatory and epistemic. The aleatory is actually intrinsic of the rock mass, of the ground mass in general. There are spatial variations, for example, joint strength, degree of weathering, and temporal variations, like, for example, the groundwater level, and these are intrinsic of the rock mass, of the ground mass. The more we investigate, we cannot decrease, because this is actually part of one property of the ground mass. But on the other hand, we have epistemic uncertainty, and this one we can handle better, because there are three types of, we could say in general, three types of epistemic uncertainty. Site characterization, for example, sampling. The sampling process can be improved to get a better understanding about what the ground mass is. The model, for example, a strength criterion or a geological model, as I showed in the previous slides. We can just be interpreting with a wrong strength criterion, which is not adequate for the ground mass. And this is a typical problem that can be solved, but a problem of epistemic character. Parameters, for example, empirical inputs for a strength parameter, which can be, we can be doing mistakes if we do not take the proper source of information. Aleatory uncertainty, as I said, it's the natural randomness of the geological process of formation, and we cannot do anything about decreasing that. They are, as I mentioned, temporal and spatial variations. They cannot be eliminated or reduced. Even with more investigation, we cannot reduce them. can be characterized by stochastic models and handled with probabilistic theory. On the other hand, epistemic uncertainty, we have some statistical uncertainty, limited information such as number of samples, available samples, and if we increase the number of samples, for example, we can decrease the epistemic uncertainty. The measurement of uncertainty, for example, if we are using inaccurate instruments, we can improve by using the adequate instruments. We can improve by using a proper model, a proper geological model that can decrease the uncertainty. And so the epistemic uncertainty can be reduced or even eliminated with more information. And it can be handled not with probabilistic models, but with fuzzy logic. Quantitative consequences. People have collected information like this one proposed by Celada. What happened in the project after we know that we only spent about 0.5% of the cost of the project in investigation, and Elena mentioned very nicely that this number should be about 3%. So see what the consequences are when someone uses only 0.5% of the investigation. There can be increases of compiled examples, not theoretical, but compiled examples of increasing the cost of the work all the way up to 80%. Of course, the more investigation we have, the lower scatter we have in these final costs. This is similar information compiled by Peila. Here we have the target predicted cost, which would be 100% if we would reach the target of the project prediction. And with less than 1%, we also see a large scatter of final cost, also reaching about 80% increase when someone was very cheap, maybe spending only 0.2% in investigation. Whereas when you have above 3%, the scatter is decreased. So this is data, this is real, this is not theoretical. So it's a big mistake saving in investigation. Harvey Parker brought us very nice suggestions. It's no longer sufficient to describe stratigraphy and groundwater table. We have to go all the way to predict the behavior, expected behavior of the rock mass. And we must also establish baseline numbers of the properties so that changed conditions, if encountered, can be administered fairly. Elena Chiriotti has just talked a lot about these contractual consequences of dealing with uncertainty. I don't have to go farther into that. So in 1984, the US National Committee on Tunneling Technology produced a very nice recommendation about investigation. And they said very clearly that expenditures in geotechnical investigations should be about 3% of estimated cost of the project, as Elena mentioned. And the boring length should be 1.0 linear meter of borehole per root meter of urban tunnel. In other words, we have a 1,000 meter tunnel in an urban area. We should have 1,500 meters of boreholes, which is not enough, I would say, to my understanding, because this 1.5 meter per meter length of tunnel would lead to only 0.001% of volume of material, which would be bored, which would be sampled. Whereas if we go to other disciplines in civil engineering, for example, concrete, I took the Brazilian standard for sprayed concrete, and we should test 0.12% of the total concrete, which is an industrialized material. And we, dealing with natural material, we are happy with seeing only 0.001. So people in concrete, they test 100 times more than what we are happy to sample. This is very little. In other words, the recommendations by the US National Committee on Tunneling Technology, I think that it should be even revised, and it should increase to have more investigation. Excavation safety and geotechnical uncertainty. How to deal with that? Probabilistic assessment of safety. And to illustrate this, I'm bringing you an example, a real example of a tunnel in the city of Campinas, very close to where I am in São Paulo. This tunnel was excavated by top heading and bench, but when it was only excavated, only the top heading was excavated without a temporary invert. It had an elephant foot. There were some problems between the contractor and the city, and the construction stopped for quite some time. Then the attorneys came to the city and asked, is it safe to have this tunnel partially open, train on top, houses and so on? Is it safe? Of course, the city could not answer that. The city hired me to answer that. How am I going to answer that with a number, factor of safety 2.5? You can wait for 100 years for this work to be completed? No, I didn't do that. I did a probabilistic evaluation of safety. There was this train on, the construction was stopped for about 1 year. And the question was, how safe is it? Unfinished tunnel, top heading shell only. 2 failure modes were analyzed: failure of the shotcrete shell and failure of the footings supporting the shotcrete shell. Evaluation of failure probability. We could quantify the variability of the soil strength, cohesion, and friction angle, published in the literature what the uncertainty for that type of soil was. And for the shotcrete, we investigated, and we could have the variability of the thickness and of the uniaxial compressive strength. We ran a 3D finite element model with a load train here on top with the values from the Brazilian code for the load train. And these are the parameters for the soil. And we adopted the load resistance factor design. We know that we know that both load and resistance follow approximately normal distributions. What we call factor of safety is simply the ratio between the average of those two distributions. The reliability index is given here as a function of average results and standard deviations of the two probabilities. And we can also define the margin of safety, which is a difference between resistance and load effects. And in this distribution, we can call this function Z. The area below 0 is exactly the probability of failure, and the probability index is given by this expression, in which we can put the factor of safety here with very simple algebraic manipulation. From the results of that 3D analysis, we had distributions of axial forces and bending moments. And for resistance histograms of shotcrete, we have had this distribution of thickness. Sorry, there is a mistake here. The average thickness is 17.5 centimeters approximately. This is wrong, not for 40.1 megapascal. I'm going to correct this and to send this PDF to you. The distribution of strength is given here, average and coefficient of variation. So we could run Monte Carlo simulation of thrust interaction diagrams, knowing the pairs of values of moment, bending moments, and normal force. We ran Monte Carlo simulation of the interaction of the moment thrust interaction diagrams to come up with the conclusion that the probability of failure of the arch was very low, actually, 1 to 32,000. But on the other hand, the probability of failure of the footing here, we found the factor of safety by strength reduction factor and by the expression correlating factor of safety with reliability index. We came to this lower result of probability of failure of 1 to 3,400 for this mode of failure. But this is a nice way of dealing with uncertainty rather than just assigning a factor of safety if we have a large scatter of strength. Spatial variability, concepts of geostatistics. The time is very limited, but I can show you briefly how we deal with spatial variability. The main concept of geostatistics is based on the variogram, which is actually the evolution of the variance between observations separated by a distance h here. The variance increases. The farther away we have the samples, the variance increases, and this law of variation of the variance with distance between samples is this function, the so-called variogram, in which we have these parameters, the range after a certain distance, then there is no more influence of the distance. We have just laws of regular statistics, no longer geostatics, but only regular statistics. This distance is the so-called range or amplitude. And here we have a kind of intercept, which is the so-called nugget effect. In other words, properties can vary in very short distance, because geostatistics comes from mining engineering. We know that in the grades of the ore can vary very drastically in short distances, and it increases. There are different functions for variograms. They are shown here. The most used is this spherical variogram. The example which I'm going to show you uses this expression. There can be an isotropy, of course. The variability can be larger in one direction than in other, and we can deal with this anisotropy by having different variograms in different directions. By knowing the variogram, then we can run ordinary kriging for spatial interpolation of properties, or even for error estimate. We want to know what's the error for our estimation of, for example, standard penetration test in ground mass. And this can be very useful for the optimization of additional investigation, because knowing the error, we can just plan our next investigation where the error is largest, not where the distance between boreholes is largest. The error may not be that high there, but we can plan the next borehole exactly where the error is maximum. In this ordinary kriging, we just do this interpolation in such a way that where we have information, the variance is 0, the coefficient of variation is 0, and the uncertainty, of course, is large between the points of investigation. This interpolation is doing by minimizing the variance and estimating values and estimating errors, as I mentioned. Requirements for kriging is that we should have a good fit for the variogram. We should have our variable with a normal distribution, and that there should be no significant spatial trend of that variable. Sometimes we have distributions with variables with log normal distributions. In those cases, we should have the variogram of x and log x. When we have logarithm of x, then we have a normal distribution, and we can have then we can prepare our variogram. This is a real example that I bring to you of a work which I supervised of research for underground works planning in the city of Curitiba in Brazil. So here, for example, we have one property, one variable, which is the depth of tertiary sediments. Tertiary sediments there are very competent for tunneling. So this is a variogram for the depth, which is not a normal distribution. Then we took the log, and now we have a normal distribution, and we can have the variogram. And there was an isotropy in different directions, as we can see here. And now we can have estimates. For example, depth of tertiary sediments. The scale is not so clear here, but we have 20, 30, 40 meters depth. So this is our the prediction based on geostatistics, and this is the prediction of the errors. If we want to refine, we can just do our next borehole where the errors are larger. Estimates for NSPT at 14-meter depth. Here we have the value of NSPT, and here we have the error. So also a very good guide to plan our next investigation. And based on NSPT, this planning work actually went a little bit farther, correlating NSPT with phase pressure required for a TBM to have stability during excavation of the tunnel. So the use of geostatistics was very providential for this prediction of variability of properties along the space. Concluding remarks, we have seen that epistemic uncertainty can decrease with good investigation, and this is our role to do it and how to do it, to identify where the errors are and where we should invest in improvements. Aleatory uncertainty, we cannot decrease it. It's an intrinsic property of the ground mass. So to deal with that, probabilistic methods for safety evaluation, for example, are very handy, and I showed you an example of that. Spatial variation, the role of geostatistics for this, I showed this work for planning of underground works for the city of Curitiba with geostatistics, and interpolation, which was done with kriging, which is a very good guide for optimization of new investigation. Thank you very much. And Martin, I don't know if I'm open for questions now or after the next lecture.
No, podemos hacer las consultas ahora, Tarcisio, si hay alguna consulta.
Ok.
¿Alguien tiene alguna consulta? El tema es muy interesante, muy complejo para estudiarlo un poco. Muchas gracias, Tarcisio. Creo que no hay consultas específicas. Así que muchas gracias por tu tiempo y por estar aquí con nosotros, y pasamos entonces a la siguiente disertación que ya fue anunciada. Vamos a escuchar a... Vamos a escuchar a la ingeniería civil Maud Macari, que va a hablar sobre prácticas contractuales, investigación, no, a ver, sistemas contractuales adaptados, masterización de contratos. Por favor, please, Maud, we listen to you. Welcome to our Congress.
Okay, well, thank you very much for your invitation. Do you see my screen? Is it?
Yes,
is it?
Yes, it's visible.
Okay. Okay. Is it in all the screen? Okay. Well, so thank you very much. So I will talk about contractual system and cost mastering for underground works. So yeah, after a little introduction, I will talk a bit about owner responsibilities and a bit largely about project management, and then going through different contractual practices. So I will talk about like general contractual practices, and then I will go through underground works specificities. And I will try to explain why it was really important to publish the new Emerald book that Elena talked previously. And we will see what what is the added value of this type of contract compared to other like more general types of contracts. Yeah, just as an introduction, just to bear in mind that, well, the objective of the different stakeholders is, and mainly the objective of the employer, is basically how to build good projects to build an infrastructure of a good quality with a reasonable cost and delay. And so this is all the goal of how to make your contract, is how to achieve this goal. So here, just to illustrate, is a picture of the Eurotunnel that was dig between France and England in 1987. So it was quite a big project. Okay, go further. Just to remind where, like the different step of the project. So Elena already talked about it. So usually we have first a very so opportunity design, which is useful to make the decision and allow the project manager to go if he go further for the project or no. Then we have the design phase and then the construction. And then we need to keep in mind that the operating phase is it's much longer than the construction phase. And so this is also something to bear in mind when you doing the design, and then when you think of your contract, is how to always think that you think of a project that's supposed to last over maybe 100 maybe 100 years. Well, that just for you, I go quickly just to be sure that we use the same words. And then, so I wanted to talk a bit about, a bit more larger about project management, and especially to underline the owner's responsibility. Because so before choosing the type of contract and go further in the project, they have a lot of action that the owner need to implement. And first of all, you need to verify the feasibility of his project. But so what we have in mind when we talk about feasibility. So first of all, it is really important that the owner defines the objectives of the project and also precise the owner's requirements. Then when we're talking about feasibility, for sure, we're talking about technical feasibility, but it is also really important to talk about financial feasibility. And so for that, we need to have a budget, and then it is one of the objectives to respect the budget. And the last point of the owner responsibility is to decide the scheme of procurement, and especially which type of contract it is adapted to implement. So I go a bit further on this different elements. So first of all, the owner's requirement. So it is really important that the owner is clear about his requirements. So first of all, define the objective, so the scope of the object, and especially the lifetime. So for example, you don't design the same tunnel if it's supposed to last like maybe 10 years or 100 years. So it is really important to specify how long your tunnel and all the equipment that are inside should last. It is also important to be really clear about functionality, availability, and quality of the infrastructure. And also really important point for transport tunnel is the level of safety. When you, for the operating period. And then, the owner, it is really also important to have the most information as possible relative to the constraint of the sites before having your work contract. And so I will definitely go a bit more into that point. Okay, and it is also the responsibility of the owner to take into account social and inhabitant concern. Regarding the budget, so this is definitely the owner responsibility. And so it needs to define the cost of investment, but also the life cycle cost. And depending on how it is operating, it might get some operation revenue, and then is able to calculate the return on, well, the estimate return on investment, which is usually depend on the date of commissioning. Okay, so let's talk a bit about the cost of investment. So usually what we include in the cost of investment, so it's all the cost of the design. So basically how much you paid your engineer that do the design, and also all the ground investigation. So Professor Celestino talked before about ground investigation, which is really important. And it is so really important to set a budget for that. You may have also the land cost if you need to buy some land, so to make your project. And then we have what we called the reference cost of the work, which is usually for methodical aspect divided in 3 parts. So first of all, you have what we call the technical estimation of the construction cost, which should be reasonably conservative. Then you usually have an advance to cover all the inaccuracies. And then you have a provision for identify risks. And then out of the reference cost of the work, you should also have, well, the owner should also have a provision for unidentified risk. Then if I go, so this graph shows how the reference cost of the work, so we're talking about this part of the estimation, how it is spread between the 3 parts as soon as the design go further in detail. So usually at the early stage of the design, you may have, well, for sure you will have an important part to cover all inaccuracies because the design is still like preliminary design, not very detailed. But you may also have an important part for the identify provision risk. And here, then when you go further in the design, it is really important to implement a risk management process, as it was presented before by Elena. And it has 2 main goals. So first of all, it will, if you implement this process, you will be able to, it will be easier to spot which ground investigation should be really, how do you say, should be the most important. So if you go through the process and you will identify, for example, maybe it will help you to spot the very high risk with a really high level of risk, and then you will want to invest money on this specific risk to try to mitigate, to have to improve the knowledge of these risks. And then the risk management process is also very useful to help to estimate the provision for identify risk. So it will, all the idea of all the process is really to identify the uncertainties. Then you make your design, you try to have a design that tackle the risk you have identified. And then, as it was said, I think by Professor Peila, you have the risk, the residual risk. And then if you can associate to this residual risk financial provision. And then this is what we call, and then if you then you can calculate the provision for identify risk. And so as further you go in the design, you will be able to be more precise and reduce the part of the budget reserved to cover the inaccuracies. And also you can hope that as soon as you go further in the design, you have more knowledge of the under the subsurface condition, and so you better your project is better. You have less risk. And then, so the last point of the owner responsibility is finally to decide the scheme of procurement and operation. So we are here in the phase of the project where all the definition and preliminary, well, some design have been done, and then so what type of contract for work do you want to choose? So I will show you the largely used different type of contracts. And so there's different type of contracts that depending on so the number of partners the employer wants to work with, the level of direct influence the owner wants to have on the construction activities, and the risk capability of the owner's organization. So I will show you the different type of contracts, and then at the end we will go back on the risk and how to choose which type of contract is adapted or not, depend on the level of risk you have on your project. So I will, so here we have like the main type of worldwide contract, and I will go through this different type of contract. Just to know that, so the International Federation of Consulting Engineers, FIDICS, provide different standard forms of contracts. So if you want, if you need models of contract, you can go on, you can buy it from the FIDIC. Here, just a graph to compare these different type of contracts. So first, so here in columns, the different contractual schemes, and here in lines, the different step of a project. So the first difference we can see is there's different types of contracts are not it is not the same level of design before. I'm sorry, I'm losing my English. So depending on the type of contract, you go further. You need to go further in the detail, in the design, before signing your contract. So this one, so the design build contract is a contract where the most of the design is well, the employers take the responsibility of all the design. So he's usually relied on designer team, which is engineers, but he bears the responsibility of it. And then the contractor only do the work. And usually the owner take back the operation. Then you have the design and build contract. So in this type of contract, the contractor assumes the detailed design and the work. So he take a bit more responsibility in the project. Then you have what we call engineer, procure and construct, which is also named turnkey contract. And in this case, the responsibility of the contractor is even bigger, and usually it starts in early stage of the design. And this last type of contract is when the owner chooses to transfer also the operation to the contractor. I will try to go quickly here. Yeah, here just to precise that in the first type of contract, so is usually the contract is usually supervised by an engineer, which is qualified in the field of the work. And usually the payment is determined by measurement, so applying the rate and prices in bill of quantities. And important to note that the employer in this type of contract assumes the unforeseeable physical conditions. Here, well, just an example to a project which was done under this type of contract. So is a part in Switzerland and France, and it was done for the research field. For it's an installation for scientific purpose. And the object of the work was to extend all the logistical parts to put some more scientific instruments. So the design and build contract. So as I said, the detailed design is made by the contractor. There is still usually an engineer to supervise the work. And it's usually paid on lump sum basis. And the employer assumes unforeseeable physical condition. So it's usually paid on lump sum basis, but with some clauses to have extra remuneration. So this type of contract is also the base for what we call new engineering contracts, which are used in the UK. So, which is a contract based on design and build model, but with another type of payment system. And also here, just to give you an example of a project built with this, with the contract NEC 3 contract. So it was the Lee Tunnel, which is storm water and sewage collection system in London. Which was built between 2010 and 2016. So what we need to bear in mind for the three types of contracts is there are three contracts with a shared risk between the employer and the constructor. So in this case, the employer signed a contract at maybe a lower price, but he may have further costs when particular unusual risks actually happened. But and the advantage is that the contractor avoids pricing such risks, and which are not easy to evaluate. So the disadvantage of this contract is that the employer finally doesn't know the final price until the end of the works. And so in this case, the employer may be willing to pay more, but to have a certain price and date of completion. And so in this case, he needs to use another type of contract, which is the turnkey contract. So in this case, the design is mainly made by the contractor, based and the employer only gives the principle and basic, well, the functional basis, and on the main is only we have only all the objectives and functional requirements. So in this type of contract, there is no engineer to supervise the work, so there is only a limited control by the employer. And the payment is on lump sum basis, but only lump sum. But in this contract, it is the contractor who is supposed to assume unforeseeable difficulties. So it may be a really nice contract. You have a fixed price and a secure date of commissioning when you sign it. But actually, this is an example that was not really lucky project. So it was used for underground works for the first Gotha rail tunnel. But actually, the contractor went bankrupt, and finally, the employer was obliged to refinance the Swiss government. And in fact, actually, this type of contract is really not suitable if there is no sufficient time or information to the tender to scrutinize and check the employer requirements. And mainly, this contract is not at all suitable if the construction involves substantial work, underground work. Yeah, because as we see in all the presentation before, the underground works is there is always uncertainties, and so like a turnkey contract is definitely not a good idea to do some underground works. So it is really no recommendation to use this standard. And well, I go quite quickly for, yes, so design, build, and operate model is usually when the employer, well, the idea of this type of contract is basically to have an indirect financing, and so is usually the contractor who pays the cost on investment, and then is refunded with toll or rent. And so this is a model of concession or public-private partnership. Well, and here is just also an example of a project which uses this type of contracts. So the tunnel of the port of Miami tunnel, and it was a 35 years concession. And here, so I try to make a link between the risk assessment of a project and the type of contract you want to choose. And so what is really important to keep in mind is like the choice of contracts need to be strongly adapted to the level of risk of your project. And so in the first case, and then also you adapt the payment tool or the payment, the way of how you pay the work regarding to the level of risk of the project. And so in the first case, in the first model, if you use payment, payment is based on unit price, it's allow you to adjust the payment, and so you are able to deal with uncertainties and adapt. If you need to adapt the quantities, then the employer is able to pay. In the design and build model, so as I was saying, is usually you pay it on, the payment is based on lump sum plus what we call a different site condition clause, which means if the physical conditions are different from the contract, then the contractor is able to ask for additional payment and delay. And to use this type of contracts, it's better to have like quite a clearly defined project with limited uncertainties. So as I was saying, the turnkey project is definitely not suitable if you have uncertainties. So, and yeah, the last one is useful for if you don't have the money to invest and to pay for the construction cost, and you prefer to have indirect finance project, even though if it may be more expensive because you pay the cost of the money. And so, yeah, so let's talk about work specificity. And so which is, well, the main point that we've seen in all the presentation before, it's all about uncertainties, because this is definitely the specificity of underground works, is like you always require excavation is an unknown or partly unknown environment. And so you contract need to deal with these uncertainties. And other characteristic is that underground works usually require many workers, and also it usually required a high investment into specialized equipment. As we've seen before, for example, if you used mechanized methods of excavation with a TBM, well, the contractor need to buy the TBM, and it's quite a high investment cost at the very beginning of the project. And what is all the key point is that team and equipment mobilization time so strongly depend on subsurface physical condition. So here, it just to show you an idea of the price variation regarding the different types of ground condition. So here is data from French projects. I can't really say if the data can apply in Argentina, but well, this was from experience in France. And so what we see here is, so if you have like easy condition, ground condition that like good rock, which doesn't need a lot of support, then you are able to do the excavation quickly, and it's not so expensive. But if you have like really bad condition, and for example, you need to require divided section to go through, the cost, well, it is really longer. The rate of advancement is really slower, and the cost is much more expensive. And what I really want to underline here is between like really good condition and really bad condition, the cost can be multiplied mainly by 6. So, well, depending on the condition you encounter, it is not like plus 10% or plus 30%. So difference can be, it can be multiplied. Well, usually it can be, the cost can be multiplied by 2, 3, 4, well, at least not on the old project, but, and so it's all, this is why it is also really important to implement all a risk management process during all the design stages, to be really able to try to better know the ground condition and to design properly the excavation methods, and so also to secure the price of your project, well, the cost of your project. And this is also underlined, this scheme also underline why it is really important to invest in ground investigation, because you definitely want to know if you are mainly in this case or in this case regarding the underground geotechnical conditions. So I think this is really the key point to bear in mind, the spread of the cost regarding the underground, well, the geotechnical condition. And so this led to the recommendation made by, well, basically we have this recommendation by every tunnel association, but mainly in the ITA recommendation presented before by Elena. So it's recommended to the employer to be transparent of the data related to the subsurface condition, and to give all the information the employer have about the subsurface conditions. It is really important also in the contract to have an interpretation of the data related to the subsurface condition, and to have baseline value that set the allocation of the risk related to subsurface condition. I think we've talked a lot about baseline value in the presentation before, and it is really important to have that in your contract. And so, you know, that if you are inside the base, well, if you are inside the baseline, and so if you encounter the conditions that are described in the geological baseline reports, then this is that means that the contractor should deal with this condition. But if you are outside of this condition, then it is a responsibility to the employer to pay for the extra cost that may be that may derive from these different subsurface conditions. And so in this case, it is also really important that the contracts have a mechanism to pay the contractor in case of deviation from the GBR. And so this is exactly, there's tools that are in the Emerald book. So which was published by the FIDIC and ITA in 2019, which was, the redaction was, well, the chairman of the group was Matthias Neuschwander, and Elena was part of the reviewer of the book. And so, yeah, so this standard form of contract really take into account the underground work specificities and provide specific tools that are able to deal with mainly with uncertainties. And so, and I think, yeah, the most important key point, well, the key point of this type of contract is to have a really clear risk allocation between the employer and the contractor. So I'll let you use the definition, but yeah, I think this is a really important message to bear in mind, is to have a fair risk allocation. Yeah, and here, just to also show you an example of a project that used a contract. It is not the Emerald book, but it's really close to Emerald book. So this is a TELT, a project between France and Italy, with an international railway tunnel, which, yeah, so up. So yeah, just to give you the concept of a tunnel and just some pictures. Well, I think Professor Peila had some, well, and yeah. And so just here to show you that it was really difficult condition that has been encountered. And so in this case, it was really important to have a tool to deal with those uncertainties, to have payment mechanisms to adapt to all the physical condition that was encountered. Yes, and so in, especially for long and deep tunnel, the Emerald book is really well adapted with specific tools that give you a way of payment to be able to finish your work with a shared risk between the contractor and the employer. And here's some recommendation, but I think Elena cites the most of it. So thank you very much for your attention. And if you have some question, will be happy to answer it.
Thank you, Maud. Thank you very much. ¿Hay alguna consulta? Thank you very much. There are no further questions. And
you're welcome.
Thank you for the presentation, and bye-bye.
Thank you.